show our sponsors, without whom we would be nowhere. So our California Edison in particular. I'd like to thank Bose Sound Systems for sending us here. And the other thing is that Joe Bubernak of the Ed Storm Group did the electroplating of the PD thin films on the silver substrate for us. Okay. This is a schematic of the calorimeter itself. And one feature you notice is that we do have a recombiner here, palladium nickel combination, and also it does have a magnetic stir at the bottom. This thing, of course, is insulated with styrofoam, and the styrofoam isn't shown there. And we have a new computerized data acquisition system, Mac 2X computer equipped with LabVIEW 2 software, used to log the cell's current, voltage, for temperature readings, in addition to computing and displaying electrical power input, thermal power output, excess power, and temperature differences. I'm going to show you now a typical front panel display. So here is a typical front panel display. And in fact, you can see that we have the calibration curve showing. Here in this region right here, there's a net endothermic reaction. When you're on the calibration curve, things are breaking even when the point is above. It means that we have a net exothermal reaction. But you can see that the input power is listed, the output power is listed, the excess, of course, is the difference between those. This thing can be set to log here. It will set to log every 6 minutes, basically. Okay, 360 seconds. When we're taking data by hand also, we set that for 15 seconds, so we get read out into the memory every 15 seconds. Okay, very nice system. I should say that Miller Bush was involved with that too. My son Roger, a genuine genius from UCLA, just graduated, and he helped us really set that computerized data acquisition system up. This gives you a summary of the thin films. I want to emphasize that we have not run a lot of these, so I'm not speaking to you today from a statistical basis. I suppose if we had a lot more money and we're a bigger school, we probably would have run hundreds of these things by now. But basically what I'm going to tell you today is very preliminary. It's just based on 6. And you can see that in the case of the cell number 26 here, we have 60 micron palladium electroplated. Again, this was done in Los Alamos onto a silver substrate. This was on anneal, and this was one of the more successful ones. Cell 27, we have 40 micron palladium electroplated onto silver. All these were electroplated or sputtered on silver. This was anneal. Didn't work terribly well. You know, a lot of excess heat. We had a 10 to 20 micron palladium electroplated in silver that was anneal. This gave nothing at all, but again, this was a water blend. We ran it with 1/10 molar LiOH. Then we had several sputtered samples, a 10 micron palladium depth sputtered on silver. This was unannealed. These samples did not look great, so we didn't really anticipate that we were going to get anything from them. The fifth one is a 5 millimicron PD sputtered on silver. This was on a needle. We got nothing from that. Finally, the one that I consider the most successful is the latest one, the 5 millimicron PD electroplated onto silver and unannealed. Okay, and the unannealed samples were the ones that were the best. In fact, of the 2 unannealed electroplated, both of those gave excess power and excess heat. So I guess we could say that with that subgroup, we had 100% success. Again, it's a little bit misleading to speak statistically when you only have the 6 samples, I realize. Okay, this is that 60 micron one was relatively successful. This was the calibration curve. It looks quite straight. And it was, in fact, regression analysis was used to fit this to a polynomial. But it does look quite straight. The error bars actually would be in the squares on that. And here is some data from the memory of the computerized data acquisition system. And this, in fact, is the calibration data. And it lists all the temperatures, the currents, and powers, what have you, the times on that. And then we have a sample data. When we were getting endothermal reaction, you see most of these are negative. So here we have the dot still below the calibration curve on the screen. If we go over to the later date where we have positive power, you can see that now we're getting positive excess power here. This is building up. Then this thing recalibrated at the end. We did a calibration check, and it calibrated quite nicely. Kind of spoiled us. We've got very good recalibration results on these. Here's kind of a summary of this. This ended up giving about 8/10 of a megajoule of excess heat. That works out in terms of a small amount of palladium, about, let's see, 4.5 times 5, okay, about 24 milligrams of palladium. So it works out to approximately, 27, around 30 watts per cubic centimeters of palladium in terms of the average power. So interesting, but not real spectacular. I might say that the only reason this one really went down was the fact that we had this one thermostat at the time. We needed to do some other experiments, and we thought we could casually put this back on low charge, calibrate some additional cells, get them ready to charge. We put this on low charge. We never were able to get it up again. So when we did get the 5-micron cell up, the unannealed one, and here's the calibration curve for that. See, very nice curve again, fitted to a polynomial using a regression analysis. When we did get that one up, I told Eagleton, I said, don't change the current, don't change the voltage, just let it go and see how much excess heat we can get if we can get excess heat. This shows calibration data from that. Slide is a little fuzzy, sorry about that. And here is some data showing that we, at this stage, still had on the 19th of April an endothermic reaction, essentially. Okay, going on over, this is showing definitely positive excess power. We now had an exothermic thermal reaction in the cell. And finally then, when we went to recalibrate this, this was a little disappointing because it only recalibrated to within about a watt. Usually we're used to about a quarter of a watt or even less. So the question is, why did it just recalibrate to a watt? I might say that at this stage, when we went to check the calibration, it had run basically for 54 days, showing excess power for essentially 54 days and excess heat for 50 of those days. It charged for 3 weeks. And of course, that's a big mystery right there. John Bacchus phoned me and talked to me about this particular cell. He said, Bob, he said, quite the most remarkable thing you've told me is that with this tiny, this very thin film, thickness only 5 microns, it took you 3 weeks to get this thing going. So when in fact it should have charged, loaded in matters of minutes, essentially. And basically, we did start looking for excess power after about a half an hour. Okay, now why did it recalibrate? Well, let me show you this excess power versus time curve. Okay, so you can see that here, which was the 0 point on this thing was about May 5th, and this rapidly climbed up to about 7 watts of excess power. And over here on the 2nd of May, we had a little explosion, a hydrogen explosion. Basically what happened is that we were running the cell, we looked at it one day, the thing was bubbling like mad, which meant the recombiner wasn't working all that efficiently. Dr. Eagleton tried to put some more recombiner in, just a small amount, to get the recombining reaction going better. And at that time there was an explosion, so the thermocouple readings jumped to it, both said, oh my God, this thing probably is not going to recalibrate. But we decided to run it. And then as it started to climb here, we essentially became braver and thought, well, let's just let it go. And so here we are, extended out here, you are 54 days later. So, and the total integrated excess heat under this power versus time curve turned out to be about 19 megajoules, which is quite exceptional. In fact, for that tiny amount of palladium, again, about 24 milligrams of palladium, you're talking on the order of roughly of about 80 gigajoules, not megajoules, 80 gigajoules per mole of palladium. Because one immediate question is silver blank, so I can't tell you if the silver is involved. If the silver were involved, it would be a lot less. Obviously, it wouldn't be spectacular from that extent. It would still be spectacular. And we all know silver is a lot cheaper. It would be a lot more economical. So we win either way. I talked to Talbot Chubb in his model. He and Scott Chubb have a model where silver should do very nicely for this sort of thing, that band theory model. And they feel my TRM model is close to theirs, so I said, well, I think I win either way on this. If it's in the palladium, I predicted the thin film effect, and I think I win that way. On the other hand, if it's in the silver, then you claim my model is a rough approximation to your band model, so I'm very happy about this. And Chubb actually came out and ran with us one day and wanted to look at this before he came to this meeting, and he in fact goaded us to recalibrate this thing. You can imagine, here we are spewing out heat like that. Everybody else is complaining about getting no data. We have more data than we can manage. I mean, it's just when these things start to go, you get unbelievable amounts of data. And he goaded us into to recalibrating, and it was a good thing he did, because later we found that the heater wire was just about to go. In fact, after we did recalibrate, we found that it only recalibrated with a watt. When we tried to get the cell up again and do another calibration preparatory to bringing the cell up, we were unable to get any power at all through the heater wire, and found out, in fact, that a small tear developed in the Teflon sleeve, and the wire had been corroded. So thank God for Talbot showing up when he did, or we wouldn't have even been able to do the first calibration check. We'd have no idea where we were. Oops. Okay, so as I say, I think on these measurements, if you take the baseline to be a watt, then we're in good shape. So rather than the 19 megajoules, if you subtract a watt day for each day, then you get back to about 15 megajoules, which is still an enormous amount of excess heat. Now this is the current versus the time curve, and the current gradually fell off because we were voltage regulating this. And I suppose the resistance of this thing was going up due to changes taking place at the surface and inside the cathode. So the current was gradually going down. It went down from a total current of about 1.2 amps down to about half an amp or so. Okay. This is data showing excess power versus current density. And here's excess power over here, current density. And you can see this looks roughly linear. And to support my contention of the 1 watt being the actual zero baseline of this, here is that data again. And I have taken a curve and extrapolated this down to the 1 watt level. And you can see that this falls at roughly 60 milliamps per centimeter square, which is about where our excess powers typically die out. Just to show you that, I've got data from an earlier cell that we did in one of our papers, and you can see that, if I get it straightened out, that here, in fact, this thing does die out between 50 and 100, so that's a typical die-out point. So I think that my assumption that the 1 watt level is the zero power base is probably pretty good. Now, is this relation between the power, the excess power, and current density linear? As you know, in my fusion technology paper in March, I've talked about the importance of the nonlinearities, the fine structure, so to speak, if you take a larger mass or finer mesh of data points. And here's an example of this. Look at this. This certainly, it was linear, sort of, if you look at the whole thing, but if you look at small regions of it, it certainly is not linear. Look at this sort of thing here. Okay? So on a smaller scale, a finer mesh of data points, these nonlinearities show up, and I urge you, if you are doing calorimetry, to try to demonstrate this. I think this is extremely important, and it would be the signature of this transmission resonance process that I talked about in that paper. Okay. Now, here's an interesting curve of the percent excess power versus time. What we've done here is taken the percent, the excess power, and divide by input power, multiply times 100%, graph versus time. How many minutes is in here? But I can't see. I have 2 minutes. Great. 2 minutes. Fine. Okay. So you can see this thing oscillates. I'm going to go very fast now. Okay, this thing oscillates. How can we count for that? Well, with TRM, if you look back at that paper of mine, I have a curve which looks like this. This is a curve of the heat, okay, the excess power versus overpotential. If the overpotential were changing in time, say linearly, then this would be a curve of overpotential versus time. What I think is happening with this curve right here, where we aren't seeing the excess power start from around zero back here and climb up, is that we are going up here on the edge of this thing. We are starting to climb, and eventually we reach a sort of a maximum height, and then we start to go downhill. And you can see with this thing, we start to go downhill here. This would eventually end up down here somewhere. We don't know how the overpotential actually evolved in time, so it's a little bit hard to account for this stuff out here. But you'll have to admit the first stuff looks like my guess has a pretty good basis for it. Now, the transmission, there's another picture of that. Picture of my kids. Here's a here's a transmission resonance model with these bands where if the deuterons hitting the surface line of these bands, they have a chance of involving themselves in the transmission resonance process. Here is a thing which explains Dr. Bacchus's pointed question of why it takes 3 weeks to load, in quotes, a 5-micron thick film. And you can look at this curve in my paper and explains it. One thing in my paper, though, I make a mistake in talking about the hydrogen overvoltage as a concentration overpotential. It's an activation. It's a hydrogen activation overpotential. So when you read that, change that in the paper. But the point of it is that if you are on a smooth palladium curve, that is, if your palladium looks shiny, you're not going to get any result at all. I should conclude now. Okay. Well, I'm just going to conclude on this one note. Okay. I'm going to summarize I'm going to give an advertisement on the neutrons. We found what we think are some thermal neutrons. I have a poster on the neutrons, okay? And Professor Tsarev talked this morning about neutrons with palladium chips, I guess, at minus 120 degrees C. I think I found his neutrons for him. This shows my model. This is temperature. This over here is relative to the number of neutrons. You should see the neutron count rate, if you will. You can see that minus 120 C is about 153 K. This is the peak I get. Tsarev, Franco, it's not at 153. Go back and look. It's actually at 147. That's the center of that, if you go back and look real carefully. I have a paper coming out of here, George Miley. That is the first part of it. Here is the minus 30 degree centigrade line that is so famous. Everybody has found. And here you can see the center is at 243 K, minus 30. So I will have that in a poster. Anybody can look at it if they want, and I would like to talk to anybody who's looking for neutrons. Thank you very much. Yes.
You were flashing a lot of data very fast. Right?
Yes, I was. You can see why now, too, right? Can you understand why I was flashing it very fast?
Some of those tables, we had the endothermic reactions running to the tune of about a watt or a watt and a half of negative.
Right.
What does that due to? That's one question. The second question is you had temperature swings of like a degree or a degree and a half in plus or minus 10, 15 seconds.
Big temperature swings. Okay, I think our thermocouples are a little noisy, that's what I think. But I could show you graphs that would show that the thing is very reproducible. If you want to see me afterwards, I'll show you these graphs. I can convince you that this stuff is very, very reproducible, okay? So you need to look at the data that I have rather than just letting me flash the graphs in front of you. Okay, so I'll get together with you afterwards. The endothermic reaction, we always have an endothermic reaction at the beginning. And I suppose this has to do with the loading process, right? You're tearing apart the Ds from what they're connected with to let them go in. So that would be my guess. I'm not a chemist, but that's my guess of what the endothermic reaction is. Is that what you gather it is? Sure. Now, which one of the curves as you see it. Okay, well, let's look at that later, okay? I'll be willing to look at it. Yes?
Well, the question is about the interface between palladium and silver. And the question is, would it be possible to explain the reactions and the interface between palladium and silver?
Obviously, without having run silver blanks, I can't really tell you much about that. I can't tell you if the silver was involved. I can't tell you if the silver was involved. And obviously, I can't tell you about the stage about the interface.
Yeah,
we do more work. Hopefully, we should be able to tell you more about that later on. So that would be one of the studies.
Your annealing mechanism said if you have no annealing, you have the best effect.
That's right. When we look at the annealed ones, we find that the surfaces look flaky. Okay? And so that's why we think the unannealed do much better. The other thing is that we never see any results until the cathode turns black. Okay, and that's explained by my model quite nicely. Yes. Yes.
I'm curious, the model is a one-dimensional model. Are you assuming one-dimensional periodic order in the plane parallel to the surface of the silver?
I guess the 110 direction, the 110 direction, I am taking a one-dimensional model. Okay, so I'm taking a row of interstitial deuterons and letting that be the direction. So,
okay,
remember the deuteron lattice looks similar to the plate.
So in other words, you're taking a parallel direction, and you're basically assuming that the underlying silver substrate is not dramatically altering the periodic order.
Right, we're making that assumption, yeah. And if the interface, obviously that would be true. Yeah.
Annealed sample.
The annealed samples didn't work very well. Yeah.
Well, maybe I would suggest you something. At 800 degrees for 2 hours.
That's what they were annealed at.
Yeah, it's very easy to form an alloy of lead and silver.
Mm-hmm.
And in this case, the solubility is very much dramatically decreased. The diffusivity is increased, the coefficient of diffusion. So
That I think was,
that would explain your
that could very well explain it, yes.
And probably one last question, since the time is short,
Yes.
With regard to using a differential thermal calorimetry,
Right.
you have thermocouples that I take it are quite close to the electrodes.
One thermocouple is between the heater and the wall, and the other one is between the heater and the cathode, and it's not right at the surface of the cathode.
But when it comes to running calibrations, you ran calibrations while you were still electrolyzing. Did you also run calibrations?
No, we didn't. The calibration was run prior to electrolyzing.
But when you ran a calibration
Prior to electrolyzing.
you ran a calibration after an electrolyzing, did you run it with the...
It was run prior to electrolyzing.
You didn't do any calibration with the heater while the electrolyzing was going on
No.
a higher power range. Okay, all right. Do you have any concept as to whether the electrolyzing affects the stirring and could affect the
The
calibration?
electrolyzing affects the what, I'm sorry?
The stirring of the
Why would it affect the stirring? Yeah, I don't, bubbles, I mean, you're talking about
Bubbles,
bubbles.
yes.
I think I suppose that could enter in, but it wouldn't enter in if we're not electrolyzing, right? If we're not electrolyzing at the beginning, not electrolyzing at the end, why would that enter in? It wouldn't.
Because when you're electrolyzing, it's going to affect the calibration of the whole apparatus. In other words, you should run a calibration while you're electrolyzing. And even if it's a linear system, if you use the heater to add extra power, you can still run a calibration and assure its linearity.
Okay, maybe I should talk to you afterwards. I'm not quite sure. Yeah, not run a blanks. We have run a cell with lithium gel ion, but that was one of the sputtered ones, and it was a needle, so that's not really a good blank. So we need to run more blanks. We need to run silver. We're going to run vapor deposition samples. We're going to run more sputter samples and more electroplated samples. Okay, big suggestion would obviously be to get your stuff electroplated by hand movement right now. Obviously, we suggest.
Okay, I'm sorry to capture.
The first speaker this morning is going to be Dr. Tsarev from the Lebedev Institute in Moscow, and the title of his talk is Cold Fusion Research in the USA. Dr. Tsarev.
I suggest that I should talk about the state of cold fusion studies in the Soviet Union. Offering of a special talk dedicated to Soviet scientists work seems to be quite justified because they are not well known to the Western scientific community. Meanwhile, both qualitatively and quantitatively, they bring a noticeable contribution to the long data pattern of this interesting phenomenon. It is even possible that some of them have been precursors of the cold fusion era. However, inadequate integration of our science with the Western one, aggravated by scanty telecommunication media development, has slowed down the process of exchange information not only with the outer world, but in our country too. It is sufficient to say that the first national conference on cold fusion in our country took place only recently, in March of this year. Figuratively speaking, up to now, we have been working behind the scenes and watching the play. Here, there. Yeah. And it seems to me it is time to raise the curtain. Well, this picture illustrates the cold fusion geography. The cold fusion geography in our country as it was presented at Dubna conference. These works are carried out by about 45 institutes, and the total number of laboratories which took place in these studies probably even more. However, many of them stopped or freezed their cold fusion activities after the first unsuccessful attempts and under the pressure of widespread skepticism. The cold fusion reputation suffered greatly in our country from Russian inexact experiments of initial period, widely boosted with mass media. The total number of Soviet publications on cold fusion certainly exceeds 100. Only at Dubna conference, more than 80 papers were submitted. About half of them are devoted to cold fusion experiments, about a quarter are connected with methodical and structural studies, and the rest are theoreticals. Until very recently, there was no any large-scale program called fusion in our country, and all researchers were financed from budgets of institutes. Recently, thanks to academician Baraboshkin initiative, the first all-union academical contest was organized with a quite small amount of money, about $500,000. At the present, a wider program is under discussion and preparation. The lack of any long-term financial support resulted in the fact that most of the Soviet experiments are characterized by small volume and duration. There are only a few prolonged and well-equipped experiments with good statistics aimed to high reproducibility. Calorimetric measurements were not widely spread and developed. At the same time, a number of works based on new original ideas and techniques have been done, which might have an interesting continuation. Below, I will concentrate mainly on such representative selected experiments where some new results have been obtained or some new techniques have been used for the first time. Having in mind a specific character of my talk, some historical excursuses are justified in my opinion. Due to lack of time, works of more traditional character, in spite of their importance, will be mentioned only briefly by showing the following tables, which contain practically the whole information which I know about Soviet experiments. Here is the list of here is the list of works on neutron measurements and more neutrons. And more neutrons with positive and negative results. And here is charged particle papers. And here is the list of experiments on tritium production. You probably mentioned, noticed that majority of our experiments were devoted to neutron measurements. And the overwhelming majority of published results are positive. At the same time, I know some groups who had negative results but didn't publish them. And maybe the last point, which might be interesting, some part of these results was received at the initial state of cold fusion studies, but they were published only recently in the called the second wave of interest in cold fusion in our country. It seems to be reasonable to begin the presentation of Soviet experiments on so-called nuclear mechanofusion, which development has been started by a group from Institute of Physical Chemistry a few years before the first publications on cold fusion. Now it is difficult to estimate the reliability of this data and their relation to cold fusion phenomena. If it is confirmed and if the mechanofusion and cold fusion mechanism, common nature, is proved, these experiments may be considered as a first example of cold fusion results. Okay, one of the first experiments of this group was devoted to neutron measurements during lithium deep crystal fracture. And this fracture was performed by a metal liner accelerator up to 200 meters per second. And neutrons were measured by a block of seven proportional counters immersed in a tank with silicon oil. The total efficiency was between 1 and 2%. To control their data validity, they also measured a so-called impulse background during shunting at empty tank. And the results collected during 75 shots is displayed here. Here you can see the histogram of pulse in the analyzed channels. Here is the source, and here is the signal from lithium destruction, impulse background, and here is the difference between lithium and background. Averaged over 75 shots, the result are the following. The signal was about 0.42, the background was about 0.16, so the net effect is about 0.26, and taking into account the efficiency of neutron emission, it corresponds to about 30 neutrons per fracturing act of lithium D crystal. Just as in the same way, this group performed another experiment, this time with heavy ice crystal instead of lithium D crystals. And the results is very close. The signal was 0.4, the background was about 0.15, and so it corresponds to about 15 neutrons per fraction act of heavy ice crystal. 3 years later, after the first announcement about the cold fusion results, this group returned the investigation, and this time they started in the presence of deuterium dot materials. Titanium chips, heavy water, lithium D crystals, and deuterated polypropylene were placed inside of fiber mill and tested, and the neutrons were measured. Here you can see the result of these measurements. For control their data, they also measured neutron emission for all these materials separately. And for this last case, the signal was about the background level. However, when they used the following combinations of material, they observed about 6 times the background level. And they also observed some sort of post effect for about 10 minutes after crushing was stopped. After 3 or 4 cycles, 3 minutes each, the signal fell to the background level. Precisely the same way, they make another experiment, this time with measurement of back activity in order to search for tritium production. As a reference material, they use copper, which is known as a practically non-absorbent material. And their measurements with titanium, copper water, copper deuterated polyethylene resulted in a signal which was more or less about the background level. However, for titanium and heavy water, titanium and deuterated polypropylene, the signal was about 1.5 the background level. The next experiment was neutron measurements in course of friction. In this case, deuterated polyethylene and heavy water were placed inside of 2 titanium surfaces, and the upper was pressed and rotated, and they measured neutrons. First of all, they observed that for the following combinations, titanium, heavy water, titanium, polyethylene, heavy water, titanium, the signal was practically at the background level. However, for the following combination, when they used preliminary cooled with nitrogen of titanium pieces of the apparatus, they observed an effect which was about 5 times the background level. They also observed a post effect for about 10 minutes, and this post effect was especially large when they used additional cooling with liquid nitrogen. The next experiment of this group was connected with measurement of neutrons from mechanically activated surface. Deuterated titanium and latent nickel-5 were ground with abrasive glue and then moistened with heavy water. And 4 to 5 sigmas effect in neutron emission was observed above the background level. However, they didn't observe any excess for the following combinations. The last experiment of this group is neutron measurements during cavitation. Titanium vibrator was immersed in heavy water, and after about 20 hours of running, they observed some excess of neutron emission above the background level. After vibration was stopped, there was no any post effect in this case. When they a little bit this material, they observed practically the same. There was effect and there was no cost effect. However, when they used not deuterated lanthanum nickel fiber, the situation was different. There was no effect in this case. However, there was a cost effect. All their results are interpreted by authors as a consequence of mechanically catalyzed decomposition of heavy water, production and fraction of hydrides. In fact, the experimental situation with nuclear mechanofusion is not clear now, it seems to me. There is some confirmation from another Soviet group. However, there are two negative results obtained by American scientists who studied lithium D crystal and heavy ice crystal fracture. And they put an upper limit which is about 15 or 25 times lower than was claimed by the Soviet group. However, I would like to stress that the situation is not so simple because conditions for American experiments was not the same as for Soviet experiments, and maybe this is the reason of this difference. Just before this conference, I was informed by this group that they continue their cavitation measurements. This time, after cavitation, they used the titanium vibrator as a cathode for electrolysis of heavy water. And in this case, they observed an effect which is about 3 times the background level. And this effect is highly reproducible. Well, the next topic is nuclear chemofusion. The first evidence of neutron emission from chemical reactions has been reported by a group from Novosibirsk. The test tube in which chemical reactions occur were placed inside of a polyethylene cube with 6 neutron counters. Shielding reduced the background to this level, and they measured temperature inside of the test tube every 5 seconds. Calibration with these sources showed that the efficiency for neutrons was about 10%, and there was no signal from gammas. They used 2 different kinds of chemical reactions. First is the following one, and about 30 grams of heavy water were placed inside of a test tube, and lithium D crystals were added little by little, and they measured the intensity of neutron emission. Here you consider results of measurement with just heavy water. This is background level. And you can compare it with this picture, which displays the results of taken during chemical reactions. Blue curve indicates the rise of temperature which is connected with chemical reactions. And this rise is correlated with neutron bursts. And the ratio of number of counts during chemical reactions to the background level was about 1.7. Recently, another Soviet group from Lenin Physical Institute in Lugansk obtained preliminary data on this kind of reaction, which confirmed Novosibirsk group results. They measured both slow and fast neutron, and their results is the following. Signal to background ratio was about 2. The other reaction used by Novosibirsk group is the oxidation reduction reaction with palladium and platinum salts. And 2 kinds of salts have been used, with hydrogen and with deuterium. And they compare the results obtained with these 2 kinds of salts. Here you consider these results. Here is the results taken during chemical reactions with hydrogen-contained salts. And this is practically the background level. And in this case, they used deuterium-contained salts, and you can see the difference. The ratio between signal and background level was about 1 for hydrogen salts and 1.55 taking into account the efficiency of neutron registration corresponds to few tenths of neutrons per gram of data-rated source. And it is important to stress that these results cannot be explained just by fluctuation as is seen from this figure. Here you can see the results of long-time background measurements, which is Poisson time. And here is the results taken during reactions with data-rated source. And you can see here the excess of color. And another feature is a high reproducibility of these experiments. The next experiment, which I'd like to present, has been done by a group from Kharkov Physical Technical Institute. There are many points which make this experiment interesting. First of all, it was the first and maybe even up-to-date unique experiment where all nuclear products except helium-4 or from the diffusion were registered simultaneously and directly in one experiment. Besides, a clear dependence of temperature dependence of neutron emission was established for the first time. And in the methodical sense, it was, seems to me, the first successful experiment with application of ion implantation in cold fusion experiment. Here you can see a sketch of their setup. They use two types of target. Thin palladium films precipitated on nickel layers and titanium foils. And they use for loading neutron beams with energy up to 25 kilo-electron-volt, and they have temperature of their samples at the level of 100 Kelvin. For control of loading, they use the measurement of charged particles yield, as is illustrated in this picture, and typical saturation was about 5 for titanium and 3 for palladium. Here you can see the results of neutron measurements. They use a neutron detector which quite low efficiency, and here you can see the temperature dependence of neutron emission taken during heating and cooling experiment. You can see quite clear pattern with two bumps, which represent, in some sense, the shape of curve of thermodesorption rate. Their estimation of source was about 100 neutrons per second. They also observed some neutron excess during repeated heating of deuterated palladium in this temperature range and during cooling. And they didn't observe any neutron excess after implantation with hydrogen ions. Simultaneously with neutron measurements, they measured also charged particles with surface barrier detectors with efficiency of order of 10 to the minus 3 counts per particles. Thin nickel film on the surface of detector resulted in some broadening of line and shift line, as indicated by this number. So, use of both these features, energy loss and shift, allowed to identify the type of particles. They made their measurement during both cooling and heating, and the energy spectrum taken from 60 experiments with palladium samples and 66 experiments with titanium samples are shown in these pictures, and you can see clear peaks corresponding to proton, triton, and helium-3 emission. Their estimations of reaction constants was about 10 to the minus 19%. At the end of their paper, authors make some remarks. There are many cracks on the surface of their samples. Non-equilibrium is definitely needed for positive results with quite a high rate of temperature change. And their results on neutron emission is larger than for emission of charged particles. The next topic is correlations. In their early work, the group from Leibniz Physical Institute at Lugansk suggested to measure correlations between nuclear products, acoustic and electromagnetic signals. And starting from about the middle of 1989, this group performed a thorough study of this phenomenon. Here you can see some examples of the apparatus used by this group. Here you can see the neutron counter with counters for slow neutrons and fast neutrons, and sometimes they use also a piezoceramic chip soldered into palladium cathode to measure acoustic signal. Here is the setup used for tritium search during thermal desorption, and this setup was used for searching for triple correlations during electrolysis, and this setup was used for double correlations search during thermal desorption. In fact, some first results of this group were presented at Pro conference, so I mentioned these results only briefly. In their search for triple correlations within 10 microsecond interval, they used the following loading rate, background rate in their channels: nuclear, acoustic, and electromagnetic. And this corresponds to the probability of chance coincidences at the level of about 10 to the minus 12 per second. During a reference run with normal water for 15 hours, they didn't observe, they observed no one triple correlation. During main run with electrolysis of heavy water for 11 hours, they observed two triple correlations, and their oscillograms are schematically shown here. And the number of chance coincidences was about 10 to the minus 7. Another correlation was recorded during thermal desorption between proton burst and acoustic signal. In order to avoid some disadvantages of this first experiment, which were connected with very low statistics and the possibility of some sort of correlated background, the same group performed another experiment in well-screened low background underground laboratory of the Baksan Neutrino Observatory, which is situated at the depth of about 1,000 meters of water equivalent. And here you can see the results. During 4 hours of running, they observed 42 events of double correlations within 100 microsecond time interval between acoustic and slow neutron signals. And the number of chance coincidences was about 5. And you can see the similarity of this curve and the curve which displayed the distribution of moderation time. And this is a good confirmation of the real source of this results. Recently, the same group obtained some new preliminary data on correlation measurements. And I'll present results of only 30% which were analyzed. In general, in these new experiments, the group could measure 5 signals: from fast neutrons, from slow neutrons, from electromagnetic signals, and from two piezoceramic chips attached to the opposite ends of palladium cathodes. And here you can see the schematical view of one of the example of 4 correlations between 2 acoustic signals, fast and slow neutrons, and there is a delay time here. They collected much higher statistics than at the beginning, and here is all the total statistics for correlation between neutron and acoustic signals, and about the same statistics was collected for correlations between neutron and electromagnetic signals. Here you can see some results. This distribution of correlation times taken during electrolysis with palladium cathode. There was a correlation between slow neutron and acoustic signals. And you can compare this curve with blue curve, which was taken just in the same way, but not with palladium, but with nickel cathode. And you see that in this case there is no correlations. This picture illustrates the results of measurement of correlation between slow neutron and electromagnetic signal. Again, red is results taken from palladium cathode and blue from nickel cathode, and you can see the difference. There is some correlations for palladium cathode. This picture presents results taken with another kind of material, niobium. For this case, they used another procedure of loading from gas phase, and they used thermodesorption with pulsing temperature during the thermodesorption run. And they observed again a number of correlation events. The last results of this group seems to be interesting in one sense and quite unexpected. This time they used steel as a material for their experiment. They tried 4 different kinds of steel, and they used special procedure for deuterium loading, which was initiated by some metallurgists. They measured slow neutrons, fast neutrons, and fast slow coincidence and acoustic. And very preliminary result is the following. They really observed an effect, positive effect, which was about 3 times the background level, but only for one kind of steel. So this experiment will be continued. The next topic is gas discharge experiment. The possibility of utilization of gas discharge for loading of metals in cold fusion experiments was demonstrated in early work which has been done by a group from Institute of Metallophysics of the Academy of Science. They used standard titanium magnetic discharge pump, and they saturated with deuterium a high surface of titanium cathode, about half of square meters. And after a few hours of running, they observed an evidence of tritium production. However, this first experiment was not very much conclusive in quantitatively not conclusive. Later, this approach was used by another groups from Podolsk, from the institute with name Luch. And here you can see the schematical view of chamber which was used by this group. One of this group was concentrated mainly on tritium measurements. And they tried many different materials, and for some of them they observed quite a high rate of tritium production, which was estimated as about 10 to the 7, 10 to the 8 atoms per second. And this group claimed that they hoped to improve their precision, their apparatus, and reach even higher level of production of tritium. This group also performed contact radiography and measurement of surface beta activity, both with positive results. They also measured neutron emission during discharge, and they observed only slight excess above the background level. So their conclusion that the tritium channel much more efficient than neutron channel. The other group concentrated mainly on palladium cathodes, and they have quite high reproducibility. The main results of this group are the following. They observed quite a high rate of neutron emission. They used slow neutron detector, fast neutron detector, and activation method. So the upper limit was about 10 to the 7%. They measured neutron spectrum, and the upper limit of energy observed for neutrons was about 17 MeV. And the ratio of number of neutrons, of two groups of neutrons, low energy and high energy, varied between 2 and 20. This group also claimed an excess of heat of order of 100